Click the bell icon to get latest videos from Ekeeda.
Hello friends, this video is going to address the topic texture from the chapter representation and description for the subject digital image processing. Many of the times whenever we are dealing with the digital images, we say that the texture of this particular image is quite good, the texture of this particular image is quite this way different. So the texture term has to be addressed with respect to the representation and description if the digital image processing techniques like the segmentation have been performed onto the original image. So in this particular chapter we have already finished with the representation techniques, having the boundary following algorithm, chain coding, then the approximation of boundary using the minimum perimeter polygon, the use of signatures and the skeletons. The description we have addressed for the boundary descriptors, Fourier descriptors, shape numbers, regional descriptors, the statistical moments, and in the previous video the topological descriptors. So let us address about texture. So here we can start with our topic texture. So an important approach to the region description is actually to quantify the texture content of the image. Although no formal definition of the texture actually exists here, intuitively this descriptor provides the measures of properties such as the smoothness, coarseness and the regularity into the image regions. So very important information is definitely available with respect to this term texture, but we cannot have a straight framework for having the definition of this texture. So let us visualize one figure that shows some of the examples here. So here we have the three examples. The white square mark from the left to right, you can notice from figure A, B and C here. So here first of all we have smoothness into the figure A, the coarseness into the figure B and the regular texture into the figure C that has some kind of periodic nature. So these are the optical microscope images of, first of all for figure A, the superconductor. For the second one we have the human cholesterol that has been scanned here, and at last figure C has a scan of microprocessor. Now the three principal approaches used in our image processing to describe such different texture of the region we can have. The first one, that is statistical approach, then second one is structural approach, and the third one is spectral approach that we shall be following throughout the discussion in this particular video. So the first approach, the statistical approaches, yields the characterization of the textures as the smooth, coarse, grainy and so on. Whereas the second approach, the structural techniques, deal with the arrangement of the image primitives such as the description of the texture based on to the regularly spaced parallel lines. Whereas the third approach, spectral techniques, are based on the properties of the Fourier spectrum and that are used primarily to detect the global periodicity in an image by identifying the high energy narrow peaks into the spectrum. So we start discussing the first approach, that is statistical approaches. So here we let small z be a random variable that denotes the gray levels, and so let p of z suffix I, where I is opting the values 0, 1, 2 up to capital L minus 1, be the corresponding histogram where capital L is the number of distinct gray levels. So the nth moment of the z about the mean is given as mu suffix n as a function of z computed as the summation, where we have I is equal to 0 ranging up to capital L minus 1 operated over the multiplication of the bracket that has the power small n inverse the difference of z suffix I minus small m here, and the multiplication is with the second operand p of z suffix I. So in the above expression, the small m that we have shown is actually the mean value of z, that is the average gray level. So m can be calculated as summation with the index factor I is equal to 0 to capital L minus 1 for the multiplication of z suffix I with p as a function of z suffix I. So here mu suffix 0 is equal to 1 and mu suffix 1 is equal to 0. Now the second moment that we can also call the variance represented as sigma square as a function of z is equal to mu 2 as a function of z is of the particular importance in the texture description. So now it is a measure of gray level contrast that can be used to establish the descriptors of relative smoothness. For example, the measure can be given as capital R is equal to the computation 1 minus the ratio where we have 1 divided by 1 plus the variance sigma square as a function of z. So this measure capital R is 0 for the areas of constant intensity and approaches the value 1 for the larger values of the variance denoted as sigma square as a function of z. So because the variance values tend to be large for the grayscale images with values, for example in the range 0 to 255, it is good idea to normalize the variance to the interval 0 to 1 for the use in the above equation. So this is done by simply dividing sigma square of z by the bracket having squared, that is L minus 1. So the standard deviation is another parameter that can be represented as sigma as a function of z, also is used frequently as the measure of texture because the values of the standard deviation tend to be more intuitive to the many people. The third moment we can have the notation by mu suffix 3 of z can be computed as the summation operated for the index factor I is equal to 0 to capital L minus 1 for the multiplication of z suffix I minus m, that is having the power 3 multiplied with p as a function of z suffix I. So this is a measure of skewness of the histogram, while the fourth moment can be given as a measure of the relative flatness. The fifth and the higher moments are not so easily related to the histogram shape, but they do provide further quantitative discrimination of the texture content also. Some of the useful additional texture measurements based on to the histogram includes the measure of uniformity, and the uniformity is given by the symbol capital U calculated as the summation operated over I is equal to 0 to capital L minus 1 over p square of z suffix I. And an average entropy measure is defined as E given by minus of the summation operation I is equal to 0 to capital L minus 1 p as a function of z suffix I log to the base 2 of p of z suffix I. So because the p's has the values in the range 0 to 1 and the sum equals 1, measurement of the capital U is maximum for an image in which all the gray levels are equal and decreases from there. So entropy is the measure of variability and is 0 for the constant image. So we can constant image also said to be the signal like the DC value. So the entropy measurement will be equal to 0 here. So we discuss one example where we can have one table that uses the summary of the values of the preceding measures that we have for the three types of the textures highlighted into the previous figures. So the highlighting was with respect to the square that we have shown in every figure A, B and C. So the texture measures for the sub images shown into the previous figure, that we can have the tabulation like this. So the texture that time we have classified as smooth, coarse and rectangle with respect to the figure A, B and C. So for the mean values we have the corresponding smoothness by 82.64, the coarseness of the mean value given by 143.56, and for the regular pattern, the periodic one at the last figure, we have the mean value 99.72. The standard deviation in the respective manner is calculated as 11.79. For the second figure we have 74.63. For the third figure we have 33.73. The measurement of capital R computed for the normalized case, we have 0.002, 0.079, 0.017. The third moment that we have discussed has the values minus 0.105, minus 0.151 and 0.750 in positive for the regular case. The uniformity calculation also we have shown with the formulation, and for the three cases it has the values 0.026, 0.005, 0.013, and lastly the entropy that just now we have discussed holds the values 5.434, 7.783 and 6.674. So to look at these values, we must conclude that the entropy, the showing of the variability into the image sample, is more for the coarseness shown into the figure B. Now the discussion we carry forward, we get back to the mean that just tells us the average gray level of each region and is useful only as the rough idea of the intensity, not really the texture. The standard deviation is much more informative with respect to it. The numbers there clearly show that the first texture has significantly less variability in the gray level, that is, it is smoother than the other two textures. The same comments holds for the capital R that we have shown, because it measures essentially the same things as the standard deviation does there. The third moment generally is useful for determining the degree of symmetry of histograms and whether they are skewed to the left, that is negative value, or the right, that is positive value. Now looking at the measure of uniformity that we have shown in one of the column, we again conclude that the first sub image is smoother, that is more uniform than the rest of the images, and that the most random, that is having the lowest uniformity, corresponding to the coarse texture. Finally, the entropy values that we have discussed are in the opposite order and thus led to the same conclusion as uniformity measures has did. So measures of the textures computed using only the histogram suffer from the limitation that they carry no information regarding the relative position of the pixels with respect to each other. So we let capital P to be a position operator here, and let capital A, that is small k by small k matrix whose elements can be denoted as small a suffix ij, is the number of times that points with gray level z suffix I occur relative to the points with gray level, that is denoted as z suffix j, with the I that is greater than or equal to 1 and j that is less than or equal to k. So this is applicable for I and j, both of them here. So between 1 and k they will be ranging, and for instance consider an image with the three gray levels having z1 equal to 0, z2 is equal to 1 and z3 is equal to 2, given as follows. So here we have the representation as the first row 0 0 0 1 2, second row 1 1 0 1 1, third row 2 2 1 0 0, fourth row 1 1 0 2 0, and the last row as 0 0 1 0 1. Now defining the position operator capital P as 1 pixel to the right and 1 pixel below yields the following 3 by 3 matrix given by capital A. So capital A for this example is having the first row 4 2 1, then second row 2 3 2, and the last row 0 2 0, where for example we have A11, that is the top left position, is the number of times that a point with the label z1 is equal to 0 appears 1 pixel location below to the right of the pixel with the same gray level, and A13, that is the top right, is the number of times that particular point with the label z1 is equal to 0 appears 1 pixel location below and to the right of the point with the gray label z3 is equal to 2. The size of capital A is determined by the number of distinct gray levels into the input image. So let small n be the total number of point pairs into the image that satisfy this capital P. So if the matrix capital C is formed by dividing every element of capital A by small n, then C suffix ij is an estimate of the joint probability that the pair of points satisfying the capital P will have the values z suffix I and z suffix j that have been separated by comma within the parenthesis. Now the matrix capital C is called as the gray level co-occurrence matrix because capital C depends onto the capital P. The presence of the given texture pattern may be detected by choosing an appropriate positional operator capital P. So more generally, the problem is to analyze a given capital C matrix in order to categorize the texture of the region over which capital C was computed. Now a set of descriptors useful for this particular purpose includes the following. So we first of all have the maximum probability, and that is given as a computation of maximum operation with I comma j to be the variables operated over C suffix ij. We have the second, that is element difference moment of order small k, computed as the two summation operations, one with the I, one with the j, for the multiplication of I minus j to the power k with C suffix ij here. The third is the case of inverse element difference moment of order k, given as again the two summation operations, one with the respect to small I operator, one with the small j, for C suffix ij divided by the bracket I minus j having the power small k here, where I and j are unequal. Now fourth is the uniformity. So uniformity is given as again the two summation operations for I and j correspondingly operating over the square of C suffix ij. Now last is the entropy, and entropy is given as minus two summation operations for corresponding I and j variables for the multiplication of C suffix ij with the logarithm of C suffix ij to the base 2. The basic idea here to characterize the content of capital C via these descriptors. So for example, the first property gives an indication of the strongest response to the positional operator capital P. The second descriptor has the relatively low value when the high values of the capital C are near the main diagonal because the differences I minus j are smaller at that place. The third descriptor that we have shown has the opposite effect to the previous one, and the fourth descriptor is highest when C suffix ij into s are all equal. The fifth descriptor is a measure of randomness, and it achieves its highest value when all the elements of capital C are maximally random. Now using these 5 descriptors that we have discussed is to teach a system representative descriptor values for a set of different textures. The texture of unknown region is then subsequently determined by how closely its descriptors match those stored in the system memory. So we are finished with the first approach, the statistical approaches. Now we go for the second approach, that is structural approaches. Now suppose here we have a rule, the form, that is capital S that tends to AS here, so which indicates that the symbol capital S may be written as small a into capital S here, AS. So if the representation of a circle that we can find into the figure A and the meaning of circles to the right is assigned to the string of the form A and so on, the right rule we have, that is S tends to AS, allows the generation of the texture pattern that is shown into the figure B. So we have the rule that is denoted as S tends to B capital A, then we have A tends to C capital A tends to small c, capital A tends to small b capital S, and capital S tends to small a. So where the presence of AB means the circle down and the presence of C means the circle to the left. We can now generate a string of the form AAA, BCC, BAA that corresponds to a 3 by 3 matrix of circles. The larger texture patterns such as the one shown into the figure C can be generated easily in the same manner. So we have the figures A, B and C here. So figure A, that is showing us a single circle that is representing the texture primitive. Then we have the figure B here that shows the pattern generated by the rule that we have at first, S tends to small a into capital S here. And lastly, the figure C here we see that is representing a two-dimensional texture pattern generated by the earlier representation and the other rules that we have shown. Now here the basic idea can be given as a simple texture primitive can be used to form a more complex texture pattern by means of some rules that limit the number of possible arrangements of the primitives. These concepts tie at the heart of the relational descriptors that we are supposed to address as the last topic to conclude our chapter representation and description, and after that we can start with the last chapter of this subject, that is object recognition. So now the third approach with respect to the texture we shall be addressing, that is spectral approaches. So the Fourier spectrum is ideally studied and suited for describing the directionality of the periodic or almost the periodic two-dimensional patterns into an image. Now these global texture patterns, although easily distinguishable as the concentrations of the high energy burst in the spectrum, generally are quite difficult to detect with the spatial methods because of the local nature of these techniques. Here we consider the three features of the Fourier spectrum that are useful for the purpose of texture description. So the first one is prominent peaks in the spectrum given the principal direction of the texture pattern. Second is the location of the peaks into the frequency plane that gives the fundamental spatial period of the patterns. The third one, eliminating any periodic components via filtering leaves non-periodic image elements which can be described then by the statistical techniques. So the spectrum is symmetric about the origin, so only half of the frequency plane needs to be considered here. Thus, for the purpose of analysis, every periodic pattern is associated with only one peak into the spectrum rather than the two peaks. Now the detection and interpretation of the spectrum features often are simplified by expressing the spectrum into the polar coordinates to yield the function given by capital S as a function of small r comma theta, where capital S is the spectrum function, small r and theta are the variables in the coordinate system in this case. So for each direction given by theta, S as a function of r comma theta may be considered as a one-dimensional function denoted as S suffix theta as a function of r. Similarly, for each frequency denoted by r, here we have the function representation S suffix r as a function of theta is again a one-dimensional function here, and analyzing S suffix theta as a function of r for the fixed value of theta yields the behavior of the spectrum along with a radial direction from the origin, whereas analyzing S suffix r as a function of theta for the fixed value of r yields the behavior along the circle centered onto the origin. A more global description is then obtained by integrating these particular functions, and it can be given as simply S as a function of r computed as a summation with theta is equal to 0 to pi over S suffix theta as a function of r, and we have the another S as a function of theta simply computed as summation where r small, that is ranging from 1 to r suffix 0 for S suffix r as a function of theta. So here r suffix 0, that is the maximum limit of the summation operation into the second equation, is the radius of the circle that is centered around the origin. Now the result of these two equations constitutes a pair of values. Here we have the set representing s as a function of r, s as a function of theta for the each pair of coordinates r comma theta. So by varying these coordinates, we can generate the two one-dimensional functions, that is s of r and s of theta, that constitute a spectral energy description of the texture for an entire image or region under consideration. Now the descriptors of these functions themselves can be computed in order to characterize their behavior quantitatively. Descriptors typically used for this purpose are the location of the highest value, the mean, the variance of both the amplitude and the axial variations, and the distance between the mean and the highest value of the function. So we have one example here to discuss the spectral approaches, that we show a figure illustrating the use of these two equations that just now we discussed for the global texture description. So we have figure part A showing the image with periodic texture and figure B showing its corresponding spectrum. So this is the visualization. Onto the left hand side you find the image showing the periodic structure, the circles with the big size and small size having the periodicity you can notice into the image. And if you have the application of Fourier transform, simply you are switched to the frequency domain, hence the spectrum can be denoted here that you find onto the right hand side. Now the next figures, figure C and D, that shows us the plots of the functions we have final represented, that is s of r and s of theta respectively, we can notice here. So the plot of the function s of r here you find onto the left hand side, and onto the right hand side we have the plot of the function s of theta here. So the peaks and the variation into the graph you can note here. Now the plot of s of r, if you take, it is a typical structure having the high energy content near the origin, so that has been shifted toward the left hand side and progressively towards the values of the higher frequencies. Now the plot of the s of theta that we have seen onto the right hand side image shows the prominent peaks at the intervals of 45 degree, which clearly correspond to the periodicity in the texture content of the image. As an illustration of how the plot of s of theta could be used to differentiate between the two texture patterns, figure E can be given, that is showing us the another image whose texture pattern is predominantly in the horizontal and vertical directions. And next to that we have the figure F showing us the plot of function s of theta for the spectrum of this image. So here we see both the images. Onto the left hand side we have figure E, another image with different type of periodic structure you can find as some kind of net into the image scanned here, and figure F, the plot of the function s of theta you can note onto the right hand side. Now as expected, this particular plot shows the peaks at 90 degree intervals. So thus discriminating between the two texture patterns by analyzing their corresponding functions s of theta waveforms would be a straightforward approach. So I hope the three approaches, the statistical, structural and spectral, definitely has given you the clarification with the details of the texture. By the next lecture we shall be addressing the next topic in this chapter. The topic is titled moment invariants. So I hope you are definitely gained the knowledge regarding texture into the images. So if you want some more concepts to be discussed, or the practical sessions to be conducted, or the practice of miscellaneous problems, you can definitely subscribe to our Ekeeda channel. Thank you.